This is Mr. Champlin. We're looking at momentum and its conservation, Chapter 3 in the Schnick textbook, 2012 to 2013, AP Physics. Momentum is a quantity used in physics. The symbol is P. Let me get this. Oops. P, momentum, equals mass times velocity. Momentum is a vector. Momentum is the product of the object's mass and its velocity. One way you can look at momentum is graphically. You recall looking at position time graphs, and we know that the slope of a position time graph is the velocity, so it would be quite easy to calculate momentum. All you need to know is the slope, slope of those, and then you can calculate the momentum. So this is down -5 over 2. -5 over 2 is 2.5. So the velocity here between 0 and 2 is -2.5. Multiply that by 2 and you get the momentum. Do the slope of this line up 5 over 4, so that's 1 1/4 slope, times 2 is 2.5. So that's how you get those. And there's no slope here, so therefore there's no momentum here. Conservation momentum. Total momentum on an isolated system is constant. Interactions within the system do not change the system's total momentum. In terms of a formula, I would write it summation of all initial momentum equals the summation of all final momentum. And that's no matter how many objects are involved. So I give some examples. Cue ball strikes stationary ball. Momentum of the cue ball before the collision equals the momentum of both moving balls after the collision. Conservation momentum. But we do neglect friction's effect. That would be an outside system exerting a force on the objects. So, but pool balls have very little friction compared to the size of the object, the mass of the object. Rock is dropped from high elevation, so we got a rock over here, rock falling. So it looks like conservation momentum is not obeyed. Rock was sitting here, no momentum. Rock is dropped, rock starts accelerating downward. If something has momentum downward, something must have upward momentum. So what is that? That's the Earth in this case. The Earth doesn't actually fly towards the rock. Reason being, it's so much more massive than the rock, so it has a very, very slight velocity in the direction of the rock. So the system is, we consider the rock and the Earth system, but momentum is still conserved. That's the point. Collisions. We have basically two types of collisions: inelastic collisions, collisions which two or more interacting objects stick together. The most common one is like train car A moving towards stationary train car B. After the collision, they collide, and then train car A and B move off together. Okay, they are joined together. But because this object was moving to the right, and this was not moving at all, the momentum has to be after the collision to the right. So we would say, setting up the equation, PAI plus PBI equals PABF together. B was not moving initially, so this is 0. So PAI equals the sum of the momentums afterwards. Elastic collisions, a collision in which the two or more interacting objects bounce off one another. Energy and mechanical energy is conserved. Well, I just should say energy. Mechanical energy is conserved. Energy conservation we discussed later. Well, that was last year. We've already discussed conservation of energy. Here's the relationship for a situation where we have two objects. Object 1, object 2. This is stationary. After the collision, 1 and 2 are both moving. They're both moving. So this was initially moving. This was not moving. So object 1 runs into object 2. Conservation of energies occurs. After the collision, 1 and 2 both move to the right. So you use this formula. The reason I gave you the formula, though, is because in order to get this formula, it takes quite a bit of algebra in terms of conservation of energy and conservation of momentum to derive these formulas. So my recommendation is you just plug them into your calculator and then you have them. So this is the mass of the two objects involved. This is the velocity of the object, first object. This is the calculate the velocity of the first object after the collision. Then here, find the velocity of the object 2 after the collision. Alright, here we have a situation where we're graphing vertical momentum and horizontal momentum. We have this much momentum in this direction. Well, first of all, we have a firecracker. It's exploding. We're given two fragments, the two momentum fragments in this direction, this direction. So we want to find out the final momentum of the other object. Well, we know generally these are going to the right, so the other object has to go to the left to conserve momentum. Well, how much? Well, it goes up 3, over 3, up 3. And then this one goes over 1, down 4. So I'm going to go from the end of this vector. We can call that momentum A. I'm going to go over 1, down 4. So that's down here. So I'm going to draw a line. Whoops. A line to there. So the total momentum would be all the way to there. So the final momentum has to be here. So this would be considered PB. And this would be the momentum of C. This is for an explosion where nothing was moving initially before the explosion, like a firecracker. Two fragments totaled that momentum, got this, and the other fragment of the firecracker had to go to the left and up. And there's the answer. That's what I showed you. All right. I broke into different types of conservation momentum problems. These are from the textbook, the Knight textbook. We have collision, moving car collides with stationary car. That was the one I showed you earlier. An explosion, two skaters push off as an example. Non-linear, they don't have to be at right angles, or they don't have to be straight on. They can be non-right angles. So it's something like this object is going like this, another object is going like that. If they join together, they'll have to go down and to the right. So that's momentum conservation. Or also we have the firecracker type problem where you have firecracker, it explodes into three fragments. So one fragment goes this way, one goes that way, and the other one goes down. Add all these up, the momentum is 0. Alright, so here's an example problem. A stationary firecracker explodes into two pieces. 2/5 of its mass moves east. What is the velocity of the other portion? So we're going to go ahead and do this. We have our firecracker initially, and then firecracker after the collision. It's not too bad of a exploding firecracker. One is going this way, one is going this way. So conservation momentum initial equals conservation of momentum final. Before the explosion, this is obviously 0 momentum. After the explosion, we can say PA F plus PBF. So let's see if we can do this. So we could say the negative of PAF equals PBF. Come up here, negative MA. Now I'm breaking to the mass and velocity. VAF equals MB VBF. It says 2/5 of its mass moves east. So we'll call east. This is the east direction. So this B is going the east, and we want to find this velocity. So I'm going to solve for VAF. So 2/5. So I can go 2/5 M goes east at 25. So what's left over? Well, if 2/5 goes one way, then 3/5 must go the other way. And we have a negative to move this negative over here. Masses cancel. 2/5 times 3/5, so that'd be 2/5 times 25 over 1 times 5 over 3. Let's see, 5's cancel. We get negative 50 over 3. So that would be negative about 17. Wow, okay, 17 meters per second, which makes sense. This is 25, so we're relatively close in velocity.